let's talk about ultrasounds. What is ultrasounds? They are longitudinal waves, or more specifically sound waves, with frequencies between 20 kilohertz and 100 kilohertz. These frequencies or ultrasounds cannot be heard by the human ear. The reason for it is because the frequencies are too high. The human ear cannot detect these high frequencies. Then there's also other type of sound waves that we get. We get infrasound waves. This is when the sound wave has a frequency that's lower than 20 hertz. Then we call it an infrasound. And these type of sounds can be detected by elephants. So as you can see here in this illustration, elephants detect infrasound, meaning sound waves that have a frequency of less than 20 hertz. Then we get the audible frequency range. This is where the human ear can detect the frequencies. So any sound that falls within the frequency range of 20 hertz and 20 kilohertz or 20,000 hertz can be detected by the human ear. And then the other type of sound wave that we get is ultrasound waves. These waves have frequencies between 20 kilohertz and 100 kilohertz, and these sound waves cannot be detected by the human ear because the frequencies are too high, but these frequencies can be detected by some animals, for example, dogs. Just remember, once again, frequency and wavelength has an inversely proportionate relationship. So because infrasounds have a very low frequency, it means they're going to have long wavelengths. Ultrasounds, on the other hand, has high frequency, which means they're going to have short wavelengths. Now let's look at a few applications of ultrasounds. So animals, especially bats and dolphins, make use of echolocation. What's echolocation again? It's when the dolphin or the bat sends out a sound wave, and then the sound wave travels through the water or through the air, and the moment it strikes its prey or an object, the sound wave bounces back or reflects and then travels all the way back to the source again, and then the bat or the dolphin can calculate the distance from its prey or its object. Then another application in the industry, we use ultrasounds to determine the thickness of objects, to detect weak spots in metals and cracks in airplane wings, or to clean the delicate mechanisms of old-fashioned watches. In the medical field, ultrasounds are used to take sonar images of the fetus in the uterus or to determine the rate of blood flow. It's also used to break up kidney or gallstones or to clean teeth and scan for tumors or cysts. Just remember, if they're asking you for an ultrasound application specifically in the medical field, then you can only give one of these examples. And then if they ask you for an application in the industry, then you can only name one of these three, and then the same for the animals. But if they just ask you to give an application in general, then you can give any one of these examples. Let's look at how exactly an ultrasound or a sonar image is formed. So, an ultrasound is sent through the human body. So obviously we have our probe. Our probe is the source of the ultrasound wave. So the ultrasound wave is created and then it moves from the probe through the human body. Then what happens next? When it is as it moves through the body, it's going to reach boundaries between two different mediums. Let's say the boundary between muscle and fat, or between the bone and the muscle, or they've reached the boundary between amniotic fluid and fetus. So what happens the moment it reaches a boundary? So part of the wave is either being absorbed, or a part is being transmitted, and then another part is being reflected. But what exactly are we seeing on the image? We see the reflected waves, and they are detected and electronically combined to form an image of the region. So just some extra information. So once these waves reaches a boundary, there's one of three stuff that's going to happen. It's either going to be reflected or absorbed or transmitted. So here you can see the complete black, basically black holes or empty spaces. This is where the wave was completely transmitted. So nothing was reflected, so we couldn't detect anything. Here where you see the white grayish parts, the grayish parts is where there was partial reflection and partial transmission, and here where you see the bright white places, that's where the wave was 100% reflected. So once again, what a sonar stands for, it stands for sound navigation and ranging.